Alright, so in this video we're going to look at separable differential equations, and we're going to jump into this example here in a minute, but first you should know that differential equations are called differential equations because they are equations that have a differential in them or a derivative in them. So an equation that you're given that looks like this is a differential equation, and what our goal is going to be here is to come up with some understanding of the original function. And so essentially this is, for our purposes right here, this is a method of anti-differentiation. And as I mentioned in class, when you look at this derivative that I've given you right here, this is another example of a derivative that is defined in terms of two different variables. So we can think of this as an approach to undoing the implicit differentiation process. When you implicitly differentiate something, you get a derivative defined in terms of multiple variables. And so our ability to undo that is what we're looking at here. So we're undoing the result of implicit differentiation. So we're going to do this by treating our differential or our derivative as a ratio. It's the ratio of two things, dy over dt, and we're going to separate this algebraically. And then we're also going to use our initial condition in order to come up with our specific original function. So what this information here tells me is that on the original function, when you plug 0 in, you get 3 out. So the point 0.03 is on that function. We're going to use that to solve for our particular solution. This allows me to find what's called a particular solution. A particular solution is something that looks like this. A general solution would be something that looks like this. A general solution has a c value in it because we do not know what the specific antiderivative is. A particular solution doesn't have a c, it has a specific number. Okay, so let's jump in. We're going to separate this dy over dt. I'm going to multiply both sides by t, and my goal is to get the y's with the dy's and the t's with the dt's. So we're almost there. I just need to divide each side by y, and this leaves me with 1 over y dy, which is equal to negative t dt. And now this thing is just asking to be integrated because I have my my dy and my dt. This is telling me that I'm going to integrate with respect to y on the left and with respect to t on the right. And when I do this, the antiderivative of 1 over y is going to give me the natural log of y plus c. And when I anti-differentiate negative t, this is going to give me t squared and a negative 1/2 coefficient plus c. And as I mentioned, this is going to be like c1 and this is going to be c2. I mentioned this in class earlier today. I'm going to call them different things so that I can keep them separate, keep them straight from each other. And kind of the shortcut here, if you don't want to bother with c1 and c2, the shortcut would be to just put c on the side, on one side, right? Just put it on one side, because by the time you subtract them and call one of them c3, you might as well just use one of them and just call it regular old c. So notice that I put it on the side that's not with my y because I'm trying to isolate y. So to finish this, I'm remembering that the natural log of y is the same as log base e of y. So I can put this equation into exponential form from log form, and that will bring me here. So I've just found the general solution. Again, it's a general solution because I don't know the specific solution. C could be anything. I don't know what it is. And if I didn't have this extra bit of information, I would be left here. But I, in fact, do have this extra bit of information, so I can try to use that to solve for C. So now there's two ways to approach this. What I know is that When the input is 0, the output is 3. In this equation, t is my input, so I can plug in 0 for t, plug in 3 for y, and get this. And then this becomes solvable. That's all 0, so I just end up with e to the power of c is equal to 3. And so this is kind of tricky, and actually I should have said don't write this down, because this is not the best way to do this. This is what people try to do, and then they get to this point where we have e to the power of c, and it's like, well, what is c? We can solve this by putting this into log form. I can write this as log base e of 3, which is equal to c, and get ln of c, or sorry, ln of 3, and that's good. But there's a better way. There's a better way to do this, so let me show you that better way. The better way to do this is to remember that using our properties of exponents, if you have x to the power of n times x to the power of m, this is x to the power of n plus m. So what we're going to do is work backwards. We've done this once before. If we have x to the power of n plus m, I can rewrite it like this. So if we do that here, I'm going to rewrite this as e to the negative 1/2 t squared times e to the power of c is equal to y. And what I've done is I've made the term with my constant its own thing. And what I can do is I can just say that e to the power of c is going to be some new constant. It's going to be a constant. So let's just call that whole thing k. It's going to be some constant called k. So what I have now is e to the power of negative 1/2 times t squared, all multiplied by k, and this equals y. So at this point, when I plug in 0 and I plug 3 in, I'm going to end up with e to the power of 0 times k is equal to 3. And e to the power of 0 we know is 1, so I just have k is equal to 3, which is a little bit cleaner. So what I've done is instead of leaving a number up there, and again, if you plug in ln of 3 up here, that's totally fine, the natural log of 3. Or you can just take this whole thing out, and this is what I would strongly encourage you to do. Take this whole thing out and make it k, which in our case is 3. So my particular solution to this differential equation is, let me just write this over here. My particular solution is y equals 3e to the negative 1/2 t squared. All right, let's do one more super fast example here. dy dx in this case is 1 over sine of y, and my initial condition is that y of 3 is equal to pi over 2. So again, this clues me into the original function. I want to find the particular solution to which the derivative is 1 over sine of y. That's what's given there. So I want to anti-differentiate this thing. So we're going to cross multiply and rewrite this. So I've got sine of y dy is equal to 1 dx. I can integrate both of these sides. The antiderivative of sine is negative cosine. And the antiderivative of 1 is just x. The antiderivative of 1 with respect to x is x. Check that. The derivative of x should be 1, and it is. So we're good. Whoops. Now I'm going to add my c on this side. I'm adding c on the side with the x, not with the y, just like last time. So we're almost done. We just need to get y by itself and deal with this initial condition. And we can actually go ahead and deal with this thing now. This is saying that when my input of x is 3, the output is pi over 2. I can deal with it now, or I can deal with it after I've made this the arc sine. But I'd rather just deal in terms of regular cosines. So let's make this the negative cosine of y, which is pi over 2, equal to x, which is 3 plus c. And we know the cosine of pi over 2 is 0, so I've got negative 0 is equal to 3 plus c. When you subtract 3 and subtract 3, c should equal negative 3. So I can go back up here. I can go back to, whoopsies, to this guy right here. I can take the c out and make that thing a negative 3. And now I'm done almost. I can just finish this by isolating y, which I can do by, well, I suppose I should make this positive, make this negative, make this positive. I've just divided everything by -1. Then you're going to want to get y by itself by taking the inverse sine, or the cosine, the arc cosine, or the arc sine of -x plus 3. And this is all equal to y.